Hello, my name is Alexander Mardvintsev. I work at Google Research where I lead a little team that works on differentiable self-organizing systems. First, I'll talk about what's self-organization and what's differentiable programming, and then how to combine the two into what we call differentiable self-organization and why this can be useful for the ALIFE community. This presentation covers some of the results that me and my colleagues obtained over the last couple of years, and we will show how to reproduce some of them starting from scratch. This presentation builds upon publications that we submitted to the Differentiable Self-Organizing Systems thread at distill.pub journal. Main inspiration for this project comes from the presentation that's called What Bodies Think About that Professor Michael Levin gave at NeurIPS conference 2018. I recommend everyone to watch this presentation because it gives an insightful overview into cognition and information processing that happens in living systems outside of neural networks, which are typically associated with these processes. If we look at the way that nature uses to build complex functional structures, we will see that it's dramatically different from the way human technology works. Natural structures are results of collective behavior of a large number of locally communicating agents that work together towards some shared global goal. This characteristic of natural systems is often referred as self-organization. One intriguing property of self-organizing systems is that it's often almost impossible to predict the global behavior, even if we precisely know the local interaction rules, without actually executing those rules in a simulation or in the real world. One of manifestations of this property is our inability to reconstruct the organism morphology given its genome, which is referred as knowledge gap in Michael Levin's presentation. I tend to think that the obscure relation between model parameters and diverse resulting patterns in the reaction diffusion model is another manifestation of this property. It's important to understand that this difficulty to predict the final result from local interaction rules is not due to chaotic nature of the process. Quite contrary, this process is remarkably robust and capable of achieving correct target morphology even in case of large perturbations. With Differentiable Self-Organizing Systems project, we decided to aim at the opposite objective first, namely, given the desired target behavior, what is the local rule that would produce it? To achieve this, we decided to rely on a familiar tool that is often called deep learning, although we prefer the name differentiable programming. I'd like to make this presentation more or less self-contained and aiming for a wider audience, so in this section I'd like to present an overview of basic building blocks of differentiable programming or deep learning that we are going to use later to design self-organizing systems. Before proceeding to the tutorial, I'd like to mention this YouTube channel by Sebastian, I wish I knew how to pronounce his second name, where he makes some great videos on programming, but the couple of videos I'd like to mention in particular is this mini-series of how do computers work and how do computers remember, where he shows how to build more and more complex circuits up to, say, a simple arithmetics unit or simple memory cell, starting from various basic NAND gates. And this changed my view on differentiable programming a little bit, because now I tend to look at the functions that are built in my programs as components, as circuits as well. And also Sebastian has some nice videos and tutorials on coding self-organizing systems such as reaction diffusion systems or simulated slime molds. Now let's get back to differentiable programming. It all starts with functions. So function is a kind of computer program that takes some input x, does something to it, and produces an output. And this input can be a single number, a list of numbers, or some more complicated data structure that's still represented as numbers in computer memory. And we can assume that this function doesn't have state, so for every time you give particular x, it will produce the same y. I can't stop being amazed by the things that we managed to produce as computable functions over the last 10 years. For example, this can be a function that computes the sign of its argument. Given x, it returns sign of x. Or it can be a function that takes an image represented as an array of RGB pixels and decides if an image contains hot dog or not. Or it can produce a list of image areas that contain hot dogs and other objects from the list of thousands of categories that the system was trained on. Or it can even produce an image. Say, this function takes a picture, finds all horses there, and colors them as zebras. So this is still a function that can be implemented with a computer from very basic building blocks. We can easily give our stateless function a memory just by introducing additional input and output elements st and st+1. For example, f can be a controller function for a robot that takes current perception vector x and state vector st that represents robot's short-term memory and information about the current task, and produce actions vector y and st+1, which represents the robot memory at the next moment of time. And or function f can be a text processing system that inputs characters or words one by one and accumulates the meaning of the sentence in those sequences of states, and it can produce, for example, translation as a sequence of y's. We can make multiple instances of the same function work together by augmenting their inputs with input elements from their neighbors. For example, here functions can correspond to different pixels or areas of the image, and we want to apply the same operation to every image neighborhood. For example, we want to detect objects in a way that's invariant to location of this object on an image. This is how convolutional neural networks work. These functions can be chained and composed in various creative ways, and that's actually what is typically referred as layers in multi-layer neural networks. It's just stacks of these functions, one following another, or branching and then converging. But these can be also combinations of building blocks that were trained to perform different functions. Like this can be a translation system where X is a sentence in English language and F then is an encoder that encodes the English language into some intermediate representation that's decided upon during training of the system, and then this representation can be sent as an input to a variety of decoders that take it and transform into a text, say in Russian or in German. The previous slides omit one important detail. All our functions take an additional argument that's commonly represented by a Greek letter theta. This theta is called parameters or parameter vector and is actually responsible for determining what the function does. Now our function f only defines the computational structure or a computational graph or a sequence of mathematical operations that's required to compute output given the input. And this computational structure is often called model architecture. So when we hear about automatic, semi-automatic architecture search, this means the process of finding efficient computational architectures that perform tasks and more suitable for training than other architectures. But the actual role, the actual task that these architectures solve are defined by learned parameters. Typically, different model architectures are more suitable for different input modalities. For example, for images are so-called convolutional neural networks are typically used. For sequences such as languages, sequence-based models such as LSTMs were applied. But nowadays there is this new breed of so-called transformer models that happen to work pretty well for a variety of modalities. Sometimes I think of model architecture as a hardware of a neural computer, and parameters are software. So the task of programming this computer boils down to finding the right set of parameters that make this architecture do the task you want it to do. Now I'll introduce another very important component of the differentiable programming pipeline. It's called loss function. Sometimes it's also called objective function. So that's a function that takes output of the model and produces a single value that measures how bad or how good the system performs. So for classification, this can be a score that corresponds to a number of mistakes the model made, but there are very many other ways to define loss functions, and this property that it produces a single number that allows to compare different stages of model training, it gives us a great power that we can use optimization algorithms to tune model parameters theta to find models that perform better and better. But great powers come with great responsibility. So we always have to remember that loss is always a proxy for a task, and small loss value, good performance during training doesn't guarantee that the model is actually doing what we want it to do. For example, it can, if you're training a classification model, it can overfit to the data or incorporate some harmful biases that lead to incorrect or even dangerous decisions made when the system is deployed in the real world. And it's always this back and forth process of designing the loss, designing architecture that may implicitly incorporate constraints that you want your system to have, and then seeing its behavior in the real world or in held out data, and trying to figure out how to alter the loss, trying to alter the training regime, trying to alter the architecture in a way that makes model behavior closer to what you actually want it to do. So the art of differentiable programming is co-designing the model architecture, the objective function, and the training schedule, the optimization procedure that minimizes this loss function. I think I have to mention this book, Why Greatness Cannot Be Planned, by Kenneth Stanley and Joel Lehman, and the approach, the loss-based approach, is probably not the right way to find systems that are open-ended and that explore the space of possibilities. But the goal of my project wasn't the artificial life or artificial life-like systems in general, but artificial life-like systems that perform specific tasks, that do exactly what we want them to do. And that's why I think the use of loss function based approaches is appropriate here. One idea that I want to emphasize here is that the field of deep learning or differentiable programming became so popular and so fertile, in my opinion, mostly because the flexibility that you have in creative ways of combining those functional building blocks. For example, can we have one function that produces parameters that are used by another function? Yes, we can, and that's sometimes called hypernetworks. Or say, can we have multiple losses instead of one, which aren't just additive, but say different losses are used to optimize different sets of parameters, and those losses somehow interact with each other, fight with each other? Well, yes, you can. It's pretty difficult to optimize such system, but that's what essentially generative adversarial networks are. When all components are defined, we can use a variant of gradient-based optimization to minimize loss by modifying the parameters vector theta. But how do we get the gradient of loss over parameters? Here comes the procedure called automatic differentiation. And there are two flavors of it: forward mode and reverse mode. So what's the difference between them and why one is preferred to another? Imagine you have some computational graph. There are some source nodes that represent input data, there are some sink nodes that are outputs of the computation, and those intermediate nodes represent some functions that are applied to the inputs and sent downstream the graph. Some nodes have multiple inputs and multiple outputs that fan out to different nodes. Imagine we feed the system with some inputs, and the values were calculated for all the intermediate nodes and for the outputs. If we now apply a tiny change to one of the input variables, for example x, this change will propagate through the network and will be reflected in some intermediate values and outputs, for example y. The change of y divided by the corresponding change of x is called derivative of y over x. So the forward automatic differentiation allows us to fix one of the network inputs, for example x, and compute derivatives of all other intermediate values and outputs over this fixed input. In turn, reverse mode automatic differentiation allows us to fix one of the network outputs and compute derivatives of this output value over all network intermediate values and inputs. In differentiable programming, we typically have a single loss or objective value to care about, and millions or billions of input parameters which influence on the loss we want to estimate. So reverse mode automatic differentiation happens to be a natural choice. That's why it's supported by all popular differentiable programming frameworks. Computing gradient of loss over all parameters with forward differentiation is computationally intractable because we'll have to run a single pass for every parameter, and in differentiable programming we typically have very many parameters. But there are still some situations when forward mode automatic differentiation is useful, and I'm glad to see that JAX has a first-class citizen support of it. Okay, I was just corrected on Twitter. Turns out that TensorFlow also has support for forward mode automatic differentiation, and there is a long-standing issue on adding the forward mode differentiation support in PyTorch, but as far as I see, there is a lot of work going on, but as of now the issue is still not resolved. So looks like this forward mode is also finding its way to other frameworks. Before we proceed to building our own differentiable programs from basic building blocks, I want to show you one very impressive use of differentiation, G9JS library developed by Guillermo Webster. So look at this dragon curve. I can grab each endpoint and move it, but I can also pick arbitrary point in a curve and move it, and the whole thing intuitively reacts to my actions. I was very impressed by this, and the library comes with a set of examples that each of which defines some data structure that contains a set of parameters and a render function that maps these parameters into geometric primitives such as points and lines. For example, here we have x and y coordinates, and they produce 2 points at position yx and at position xy. And when we move one point, the other point moves as well. And we can get some beautiful interactions by emitting more points and we also have some pretty complex interfaces that can be implemented by just defining a number of parameters and points, and library produces interaction automatically. For example, here is this cube, so we define how to project points on screen, and the library makes the cube draggable and rotatable. And another example, this fractal tree that we can drag at arbitrary node, and it reacts and adjusts to our actions. For example, this clock, if we move the minute hand, the clock, the other one moves. So I was very impressed by this demo. I decided to look under the hood and see what's going on inside. So the source is on GitHub, and the core is essentially a gradient computation. So this library doesn't rely on automatic differentiation. It does finite differences, but the procedure is quite similar to using forward mode automatic differentiation. So the loss is the distance between the point that user is dragging and the mouse pointer, and it iterates over parameters one by one and uses finite differences to estimate the gradient or the derivative of point positions over this parameter. And I thought that it wouldn't be hard to take some like modern differentiable programming framework and reproduce this interaction. So I picked up TFGS, which is automatic differentiation framework built for the web with JS, and decided to implement some primitives and some examples with it, like this one. For example, there is a number of segments that there is a number of parameters which are turn angles between current segment and the previous one, and when we drag a point, we backpropagate to those angles. So the whole thing readjusts itself, and also I apply. You see that when I drag the endpoint, changes don't propagate through the first node, but if I drag the first node, I move the whole thing, and I use stop gradient primitive that prevents propagation of the gradient to the end node. So only when loss applied to the position of that node itself, it gets altered. And well, there is a fractal tree example as well, and with TFGS it wasn't that difficult to implement. So the core here is this my loss function, that is the distance between, well, square distance between the point that user is dragging and the mouse cursor, and just with less than 100 lines of code I implemented the interaction that is similar to G9.js. Let's look at the basic building blocks that we will use to build our differentiable programs or differentiable circuits. One type of gate is sufficient to build a whole computer. It's either NOR or NAND gate. Here I'm using three types of gates: addition, multiplication, and, well, a few different types of unary functions. And also I treat fanout or split as another type of gate, but essentially it just takes output of one gate and sends it to multiple inputs. I treat it as a separate type of gate because it will need some special handling when implementing backpropagation. But let's look at the forward propagation first. Everything is quite simple here, school level basic calculus. So we replace each value with a pair of values. One corresponds to original value and another corresponds to derivative of this value over the input node that we selected as a derivative source. So for all inputs we set this second value to 0 except for the selected node for which it is 1. And then we propagate these derivatives forward starting from source nodes. And we can also treat this process as a construction of another computational circuit that runs just in parallel with the original. Now let's look at the backpropagation automatic differentiation case. We can think of it as selecting some node at the end of the network, some output, typically it's single loss value, and then constructing auxiliary network that starts from that value and passes the gradient, so the partial derivative of this value over all other intermediate nodes. We do this by mapping the nodes that constitute the original network with their complementary backpropagation counterparts. There is interesting symmetry between addition and fan-out nodes. Addition becomes fan-out on backpropagation, and fan-out becomes addition. Backpropagation equivalent of addition receives the gradient value from the previous node that corresponds to the output of summation nodes and just passes it further upstream the network. And fan-out equivalent must sum up the gradients that correspond to fan-out outputs and pass it as a gradient of fan-out input. It's also worth pointing that gradients of these two add and fan-out nodes don't require any information from the input pass on backpropagation. They only operate with gradients. Backpropagation through multiplication operation and unary function is a little bit more involved and requires remembering values that were used during forward pass. For example, computing the gradient over A requires knowing the B, and computing the gradient over B requires knowing the value of A that was used during forward propagation. And for unary function, we need to know X to compute the derivative of function f at point X to apply the chain rule. We now have all the gates we need. We know how to differentiate from them, forward and backward. Let's build something. Let's build the workhorse of modern machine learning and deep learning and differentiable programming, the ubiquitous dense layer, which is essentially vector by matrix multiplication. So we take some input vector, two-dimensional in this case, and multiply it by 2 by 3 matrix of coefficients to produce a three-dimensional output vector. We also add bias value to each of elements of the output vector. So this is how the circuit that computes vector matrix multiplication may look like. Let's now try to build a backpropagation network for this circuit. There will be actually two backpropagation circuits. One will propagate gradients to the inputs, and the other will backpropagate gradients to parameters. And this happens because each multiplication operation actually splits into two operations on backpropagation. So first, the circuit that propagates gradients to inputs. It can be seen as a transposition of the original circuit. So all summations become fan-outs, all fan-outs became additions, and directions of all edges just reversed, well, except those that come from weights. So neat thing about this operation is that we don't need to store inputs to the circuit in order to compute gradients over those inputs, although we will need those inputs to compute gradients against weights. Backpropagation to parameters is even simpler in some sense. Gradients of the output propagate directly to biases, and the gradient of each weight of each parameter is just a multiplication of corresponding output gradient and input value. But in order to compute this type of gradient, we need to store the inputs from the forward propagation path. Networks that consist of these layers that are linear with respect to their inputs are quite restricted in the complexity of functions they can represent. No matter how many of such layers you stack, you still get a linear function against inputs. So typical method of adding complexity, adding representative power to such neural circuits is adding so-called activation functions that are interleaved with linear layers. And the choice of activation functions can be actually quite critical. And there is this anecdote that some people, for example, Christian Szigeti, who created Inception neural network architecture that was quite widely used for vision models, and also was one of the people who discovered adversarial examples and batch normalization. So he thinks that the wrong choice of activation function was the factor that largely delayed the widespread adoption of differentiable programming. So for decades people were using a function that looks like this. It's called Sigmoid, and it looks nice and smooth and seems to be very suitable for differentiable optimization. But turns out that when you stack many layers that are interleaved with these type of functions, then you get the problem of vanishing gradients when some inputs that get saturated in these flat areas of sigmoid don't propagate gradients because the derivative in these areas is very small. And turns out that Relu, which looks much simpler and much less suitable for differentiable optimization, it's not smooth around zero, but somehow it happens to work much better for differentiable programming than sigmoids and allow to train very deep, very powerful models. And on backpropagation it works as a kind of gate. So when input from forward propagation path was non-negative, it passes the gradient back as is, but if it was negative, it sets the gradient to 0. So you only need to remember the sign of the input value. By now we've discussed the design principles of differentiable programs and basic building blocks that we will use. Let's now use them to build differentiable self-organizing systems. Generally speaking, differentiable self-organizing system consists of a neural controller that is shared by a population of agents interacting on a simulated environment during a limited time span. The whole system is evaluated against an objective function that measures the proximity of the current behavior to the desired. End-to-end differentiability allows propagation of the objective gradient to the controller, steering the system behavior towards the target specification. Today we will try to implement a very minimalistic neural cell automata or neural CA model. Neural CA operates on a uniform grid. The state of each cell is represented by a number of real values, 3 of which are visible as RGB color channels. Cells iteratively update their state using the information collected from their 3x3 neighborhood. As I've promised, we are going to start from scratch. So I went to collab.research.google.com, which is a Google-provided Jupyter Notebook hosting service, and created a new notebook. I'm going to use GPU, so I'm selecting the runtime that has graphical accelerator. Pressing connect. Let's see what kind of machine did we get. Tesla P100. So I'm using a paid version of Google Colab that costs $10 per month. That's why I'm getting higher end GPUs. Sometimes I get P100, sometimes even get lucky and have a V100 GPU machine. Free version typically gets Tesla T-Force. I've told that I'm going to be coding starting from scratch, but actually I'll cheat a little bit. I will use a feature of Colab called snippets to embed some boilerplate that I typically use in my project, and you can create your own custom snippets in addition to various useful snippets that are already provided. And the way you add your custom snippets, or you can add my snippets as well, is to add URLs to notebooks that contain them into this field, into this list in settings. So I'm just removing the extra cell and copying snippet into the current notebook. It has some basic image displaying utilities. Also, it has a function to zoom image that's handy for displaying some visualizations of some matrices, and a video writer that allows to record videos right in collabs. This is what I use to generate those supplementary material videos for publications. And let's add this so that we always know which GPU do we have. Okay, I'm collapsing this cell, and we are ready to code something. By a popular vote, I'll be using PyTorch framework in this tutorial. Typically I was using TensorFlow, but when I saw that quite a few people are interested in PyTorch, I wanted to reach wider audience. So actually I tried to implement neural cell automata for texture synthesis with PyTorch, and it seemed to be fairly comparable with TensorFlow. Actually, I think two frameworks are pretty similar. And today we are going to implement the variant of the model from this article, from texture generation with neural CA, but I will show how to make a much more compact version of this model, starting from scratch, try to explain the reasoning behind design decisions. The system we will implement now will be able to take an image texture sample and produce a cell automata rule that would synthesize this texture. I will copy paste some code lines from the other hidden notebook I have, but these are going to be pretty trivial. So here I'm importing the PyTorch modules, and also I'm setting the default tensor type to GPU CUDA tensor. To be honest, I'm not a great specialist in PyTorch. I don't know if it's a good practice or not, but it worked well enough for me. Now all tensors I create reside on GPU by default. We will manipulate tensors, which are essentially high-dimensional arrays, a lot. So I am installing and importing another very useful library called INOPS. I really recommend people using it because it greatly simplifies the notation of transforming tensors, changing shapes, changing the order of axes, and so on. This library is essentially a tiny DSL for high-dimensional array manipulation. I will be using some code snippets from the PyTorch Colab notebook that accompanies the texture synthesis with neural CA article. Those are parts that aren't specific to differentiable self-organization, but just useful. For example, this loss function, this texture loss function, is based on VGG16 pre-trained neural network and replicates the classical neural algorithm for artistic style transfer paper from 2015 by Leon Gattis and Alexander Ecker. So I am just copying this code into our notebook. It will download the pre-trained model on the first run of the cell. This code block defines three useful functions. One takes a batch of images and computes gram matrices, which are texture descriptors that we will go into use to match textures. with a style loss. The second one takes two sets of text descriptors and computes squared losses against them. And the last one, which I already see can be a little bit confusing, and we will rewrite it a little bit right now. This takes a set of images which have the order of dimensions, height, width, and the last dimension of size 3 are RGB channels, and reshapes putting the channels dimension at the second place. And also, if there is only one channel, so it doesn't have batch dimension, then we expand dimensions by adding this dummy dimension of size 1 at the beginning of tensor dimensions. So I will modify this line by using our rearrange function, so that you see that it provides to express axis manipulations more explicitly. So what we did is given the array dimensions names, well, single letter names, but I hope it's a little bit more understandable than just numbers. So we say that this array has the axis of batch, height, width, and channel, and now we shuffle those axes, putting the channel at the second place. Similar to previous narrow same model, our model will use Laplacian and Sobel filters for gathering information about each cell neighborhood. So I'm copying the definitions of these filters from the supplementary notebook. But I will remove those coefficients. Somehow it works better when I don't normalize the kernels, probably because due to larger values, more gradient flows through the branch that communicates with neighborhoods during the backprop, because it's pretty speculative. But I've just noticed that I get better patterns when I don't downscale these kernels with normalization coefficients. As in previous article, each cell is going to be represented by a vector of values, and this constant will define the number of these values. So I'll use 12, which is the smallest I managed to get while not degrading the quality too much. And I'm trying to make these models as small as possible, as simple as possible, because I hope one day to be able to implement them in hardware or even in something closer to living system. In previous model, I applied 4 different filters to each channel to form the perception vector. I had this function called per channel convolution that was producing a number of outputs that equal to number of channels multiplied by the number of filters. In new model, in order to simplify things even further, I will use just one filter per channel, and so each channel gets its own filter. So I've created an array of filters. It has 4 Laplacians, 4 X Sobel, and 4 Y Sobel kernels. So first 4 channels get one filter, then another 4 channels get the other filter, and so on. And I applied Laplacian filters to first 3 channels that are also going to be interpreted as RGB channels to kind of avoid this bias towards visible channels being connected to a particular orientation of patterns. I'm not sure about that, but hopefully this partially prevents this bias towards drifting patterns that I was experiencing in my previous model, although I don't have data to back up this claim. I've created the template for the module that will actually implement cell automata rule. In constructor we will define the parameters, and the update step is going to be implemented by format function that will receive an array, a tensor that contains the state of a grid, and produce the state of the grid at the next iteration. As in previous article, we have update rate parameter that controls the fraction of cells that are going to be updated at each iteration, and this introduces an asynchronicity in our model so that we don't assume the existence of global clock, and also those stochastic updates happen to provide the source of randomness that our model will use to break the symmetry when forming patterns. So let me explain what's going on here. I decided to implement the perception phase of cell update first. So I took the input tensor, and first I want to use wraparound padding, so I want pattern that crosses the image boundary to continue from the other side of the grid, so I don't have to worry about boundary conditions. So I take the input grid and pad it in from top, bottom, left and right by 1 pixel using circular padding, so it just copies corresponding pixel from the other side of the grid, and then I use this convolution Vade operation. So it's a little bit confusing, this notation of group convolution, and I had to add additional dummy dimension to my filters array, but this boils down to applying individual filter to individual channels, and in order to test that what I did works, I created array of zeros of shape 3x3 as an input, and then set all values at position 1 1 of this array. So this is center of array to ones, and then applied my forward function and printed the wise array. So I expect that when you apply convolution to a unit pulse, you get each pulse turned into transport version of convolutional filters, and that's what I see here. So first 4 filters remain unchanged because Laplacian kernel is symmetric, and then other kernels get transposed, so minuses were here and they are here now. So looks like the new perception phase works as expected. It takes array of that with 12 channel and produces array of the same shape with 12 channels, but now these channels contain information of a neighborhood of each cell collected through those. Here is the first attempt to make an update rule for the cell automata. So we have perception vector. I concatenate this perception vector with the current state of the cell because, well, it's reasonable to assume that cell knows its own state and can use this information to perform an update. So it uses own state plus information collected about neighbor cells through those image filters, and then all I do is just as a first experiment pass this vector to convolution to deconvolution, but I'm going to use 1 by 1 filter, so it's essentially just multiplication of each element of these y corresponding to each cell by a matrix, and then adding biases. And this here I form the incremental updates vector. Those updates gets get added to current cell states, but they are multiplied by stochastic updates mask, which is just array of random values that gets transformed to like in a way that when the random value is smaller than update rate, it becomes 0, and when it's larger than update rate, it becomes 1. So all I do is this rand produces values in the range 0 to 1, I add update rate, and then I apply floor operation. And now I'll need to provide the parameters that will control the behavior of the CA. Note that we can't expect much from such a simple model because it doesn't even have any nonlinearities. So all that happens is perfectly linear, and actually when I tried this for the first time I was very surprised that I at least see some patterns emerging, and those are probably coming from the noise that comes from stochastic updates filtered by linear filters encoded in those static filters and learned metrics. Now I've created the parameter arrays for weights and biases. Biases is just an array of biases are just initialized to zeros, and weights are initialized to unit normal distribution scaled by 10 to the power minus 3, and these two ones mean that it's a convolutional filter of shape 1 by 1, which means that it doesn't have any communication with neighbors. It only considers the current cell to compute update, and it has CHN outputs and 2 CHN inputs, and these 2 corresponds to the shape number of channels in array Y, and it's multiplied by 2 because I can concatenate it 2 arrays of with 12 channels, and turns out that originally I forgot to specify the dimension number along which I'm going to concatenate. Now let's try to train this model. First we will define the loss function that will try to steer our system into producing a particular texture. I've loaded the image from a specified URL. Well, I've chosen this tribute to Mondrian image I found online, and I calculated the style descriptor for this image. It's also helpful to downscale image before computing this descriptor, because our cell automata aren't operating in super large resolutions, and it works better when textures are in that high resolution as well. Let me explain what's going on here. I've created the optimizer that we will use. I've copied the training schedule from the textures article, and in this line I'm creating a pool of states that will be used to stabilize our patterns so that they continue to produce something reasonable when there is already some non-initial state of a grid when they started the iteration. And I've added this function seed that just produces the initial state for the cell automata to operate, which is just all zeros, and also a function that converts state of a CA to RGB color image by just taking first 3 channels and adding 0.5. And to know more about this sample pool strategy, I recommend you to read the growing growing CA article where we discuss this in detail in the experiment 2 section, when we try to stabilize model, try to make it persistent. Otherwise, our cell automata were exploding after a number of iterations, becoming unstable, and that's the same behavior that we observed with texture synthesizing CAs, and used the same strategies to mitigate. I've created the loss function, and loss consists of two terms. One is style loss from the original texture style synthesis article, and then I've added another overflow loss. I find it useful to limit the range of values that state channels can take from -1 to 1, because later it's easier to quantize those models when you know the range that values are going to take, and it seems to make some of patterns more stable as well. So now I've created the batch of grid states, empty grid states, applied the loss, and well, at least it seems to return some value, it doesn't crash. Now I've implemented the training loop, and it even looks to be working, and while it runs, let me explain it line by line. I copied some snippets from the texture synthesis notebook implementation of CA training, but first let me I create a loop of 8,000 iterations, and then there is this torch no grad context. This is something that I think one of the main and a little bit annoying differences between TensorFlow and PyTorch, and this well, by default, PyTorch tries to record all operations on something like gradient tape, so it remembers which tensors were computed using which operations from which inputs, and it causes some problems sometimes. And in order to disable this behavior when you don't need to compute gradient, for example, when I extract samples from batch, or when I update the model parameters, I use this no gradient context. In TensorFlow, it's opposite. You have a special context gradient tape to when you need to compute gradients, and otherwise gradients are not tracked. Okay, so here I sample a bunch of indices in a pool. Batch size is equals to 4, and extract the grid states into the array X, and then for every 8th batch I replace the first element of this batch with the seed state, so that the model doesn't forget how to grow starting from seed. Then I sample a random number of steps and iterate the model for this number of steps starting from the grid state, where recursively applying the current CA to the state. Then I evaluate loss, and then once again I'm entering this no grad context. I propagate the gradient through the graph that PyTorch remembered for me towards network parameters, and then this trick that we are using since the Grow NCA article is pretty standard actually in deep learning world. This prevents sudden bursts of high loss leading to high gradients to destabilize the optimizer and throw it away from the current solution into region which performs very poorly. Then we perform the optimizer step and place the current states back to the pool at corresponding positions so we can reuse them on next training steps. Record the current loss value to generate this plot and render the plot, render the current batch output as color images, and some statistics on training. And what we see that our model doesn't really train. Sometimes it produces something like vertical stripes. Well, that's the reason for this is that our model is too unflexible, it's purely linear, and those stripes are nothing but noise from stochastic updates filtered by linear filter. So let's try to add some nonlinearities to our model. As a first attempt, I'm trying to add nonlinearity to our model by just taking Relu of vector y before processing it with convolution, which is just matrix multiplication. And also here I added the line that counts the number of parameters of neural CA and prints it. So right now our CA has 300 parameters, which is very small. It's more than 10 times smaller than our previous model, but I don't really expect it to work. Actually, I don't remember if I tried this particular configuration before, so let's try to run training again. I stopped training after 3 minutes or about 4 minutes, and I have to say that result is somewhat better than I expected. I at least see something that somehow reminds this pattern, and loss continues to go down, but I will extend this model a little bit to make it more powerful while using just less than 2 times more parameters and without expanding the number of feature channels. So what I do is once again a concatenation. I'm concatenating the Relu of x with this construct. I take minus y, then I take Relu, and then I take minus again. So the meaning of this is that I kind of have 2 different coefficients for each of those values. One is used for positive part of the activation range, and the other is used for negative part of the activation range. So each value is like splits into 2 channels. If it's positive, it goes into one branch. If it's negative and gets treated by one set of coefficients, if it's positive, it goes to the other branch. And now my convolution has 2 times more inputs again, so I multiply the number of inputs for this operation by 4 rather than by 2. And let's try to see how will this model train. Now we have 588 parameters. Looks much better now. After about 5 minutes of training, we have this nicely looking pattern, and while the training was going, I wrote this little code snippet that will hopefully show us this pattern in dynamics once I run it. Oh, okay, there is some problem. X, and also let's use T. A little bit too small, but I have some handy utilities. And also let's show the output on the side. So we see that we have a nice looking pattern that is stable over a very large number of iterations. Total number of steps that were made during during production of this video is almost 6,000, and I'm curious if we can increase number of steps. Will it continue to be stable? Looks like so. Now it's almost 9,000 steps that were performed to generate the video. And we see that it produces dynamic but consistent pattern. And this dynamics comes from the fact that all we want from Cellular Automata is produce a reasonable pattern that minimizes loss at every frame that we evaluated, but we don't ever specify that the pattern should be static. So by default, our Cellular Automata happens to produce a moving texture, and that's all that's required to implement and train such model. So it's pretty compact. Here is the implementation of forward procedure, and if we try to match what's going on against the building blocks that we were discussing at the beginning of this tutorial, so applying same program to multiple locations on a grid is essentially this pattern where you have multiple instances of the same function that share parameter. So you can take a global block of parameters and connect it by as an additional argument to all of these functions. And this is what used to backpropagate over time. This is called backpropagation over time, when we instantiate multiple instances of the same function but connect them in series rather than in parallel. So this run of narrow CA evolution across a number of iterations that gets unrolled into a circuit that is built out of elements that we discussed. We only use, like, if at the very basic level, it's all one of those 4 types of gates that we discussed, and backpropagation allows to find the parameters that make this self-organizing system produce a pattern that satisfies objective that we enforced. And in this visualization, this rectangle down there, I visualize weights of the metrics, because once I plotted them for the first time, I was surprised by structure that they contain. Actually, it's pretty trivial. This main diagonal of negative values is something like decay. So values of the array gradually decay, and this is probably the way the Cellular Automata stabilizes itself. So when they grow too high, these terms start to dominate, and other terms encode interaction between interaction between channels of the model, and this diagonal here probably corresponds to Laplacian filters that get applied to first few channels, and adding Laplacian filters is equivalent to blurring, so model probably learned to blur the first four channels a little bit after every iteration, a little bit at every iteration for whatever reason. I also want to make a remark about colors and why texture doesn't look exactly the same as what Cellular Automata produced in terms of color distribution. And this can be fault of Cellular Automata, but I actually think that in this particular case that's the fault of style transfer loss that we were using, because I've observed that it's not super good at reproducing blocks of solid colors. It's much better with edges and textures. And with this I'd like to end the first part of the tutorial. By now we have implemented the narrow LCA model that has less than 600 parameters, and which is almost 10 times smaller than the previous architecture that I was using for text to synthesize. It's actually so small that it can easily fit into a single JLSL shader. And let me paste one piece of code that will export it for us. This piece of code does a very interesting thing. It takes parameters of Cellular Automata, weights, biases, and exports them in a small reasonably small self-contained C function. I use some obfuscated C style coding to minimize the boilerplate code, so that the most of the code consists of quantized parameters of the model. Actually, all 588 numbers are here, and we see that this is, well, and we can take this snippet and paste it into JLSL template that I'll provide the link to, and we can make this shader execute in a shadatory environment. And let me give an idea of how compact this implementation is. So there are two passes that are being executed. The first pass computes the perception. It convolves the current state of the grid with three filters depending on the position in the frame buffer. So I can visualize the frame buffer this way. The whole frame is split into three parts, and each of which corresponds to 4 consecutive channels encoded as RGBA. And also I can visualize the perception buffer. So we see that for the first part Laplacian was applied, then vertical gradient and horizontal gradient, and then I transpose the buffer to fit it on screen. That's why vertical Sobel filter goes first, and now we only see the RGB part. And then so this is a perception shader, and this shader implements the update rule. It reads from the buffer, from buffers produced by a perception shader and original state, concatenates them into this vector, and then passes this vector to generated update function. An update function just has this gate-like structure, which, depending on the sign of corresponding input vector element, selects the coefficient that it needs to apply to this element and accumulates these these multiplication results in the update vector, and I multiplied the neural network coefficient by large numbers so that I could represent them as integers and don't waste the code space on floating point dots, and just for compactness of the C representation. And then once we computed update vector, we apply a random mask to it, the stochastic update mask, and add it to the current state. By the way, I forgot to mention one important detail about update mask that I'm using here. Let me get back to the code for Cell Automata model. So in original implementation, I was updating cells. I was updating each cell as a whole, and now I am updating each of the channels stochastically. So in a sense, granularity of synchronization decreased even further. Now every channel, every value that is stored inside of each cell can be updated independently of others. Another interesting lesson I learned while porting this shader from PyTorch or TensorFlow to GLSL is that adapting the circuit to other computational architecture allows you to resolve some ambiguities that and make design decisions that you weren't sure about. For example, from the perspective of differentiable programming, this line that doubles the number of perception vector is pretty much equivalent to, for example, this line. I can, instead of using linear combinations of negative and positive parts, I can use linear combination of y and EPS I, or I can use y and Relu y, and all of these performed comparably, and I didn't know which one to choose. But when I started implementing things with GLSL, it became apparent that with this approach I can use twice less multiplications, and in case I store textures, I store coefficients in textures but not in shader code itself, I can also reduce number of texture fetches. So this design decision was nailed by a computational substrate, the environment that I was using to implement the model. Is there anything else that our 600 parameter Cellular Automata can do beyond synthesizing textures? Let's try to figure out. I've added some imports that I'll use to generate synthetic tasks for Cellular Automata. Here is an example of inputs and outputs for the first task I tried beyond texture synthesis for this particular neural architecture. So for previous models we knew that they can classify MNIST digits, for example, but I wanted to push the limit, to find the limits of this tiny model. So this is the minimum spanning tree construction tasks. I generate a random set of points on a plane, compute minimum spanning tree, rasterize it as line segments, and then we'd like our model to take this type of images as inputs and produce output. So connect the nodes with lines, and node positions will be encoded in the first channel of the cell state. I'm going to copy the training setup code from our previous experiment, but I will replace the pool generation with populating the pool with set of tasks. Pool X is going to contain initial states, and pool y is going to contain the expected results. This function just generates an array of task pairs. And we will reuse the training code from the previous example with some modifications. So we've got training running, and let's see where will it get us. Little by little the model seems to be learning something, and I will modify the training objective a little bit because right now not drawing the line somewhere and drawing the extra line have equal loss coefficients, and I'd prefer to steer the model a little bit into area where I'd prefer to draw too many lines rather than too few. So I'll use different weights for positive and negative difference losses. And by the way, loss is now just pixel-wise squared difference between the current state of the system and the target pattern. And also I see that I've made a mistake and I'm using the wrong channel to compute loss, not the one that I visualize. So let's have a look at what the other channel looks like. It looks much better. We really see that there is something like spanning trees being produced. It's pretty early in training, but let me modify the training objective and rerun the training. So positive difference values correspond to areas where the model draw a line where it shouldn't be, and I will downweight this term a little bit, and a negative will stay as it is. And yes, I'll be using the zeros channel for input and output. So the training is started. Let's see where it will get us now. So the training was actually running during we were watching the videos, and I can show some pretty interesting things. So let me now present the notebook, and we will play a little bit with it. Yes. So we actually see that after 8,000 of steps, model have converged into producing something that connects the points, at least. Well, it doesn't look like spanning tree, but it's something. And we see that there are those like roots spanning through the boundaries, and I understood that I made a little mistake. In my previous experiments, I wasn't using for spanning tree task, I wasn't using the wraparound boundary. I was deliberately setting the boundary to 0 because I wanted to the objective to be well defined. Otherwise, it's all translation invariant, and the model just doesn't know where the grid ends, and it shouldn't connect to further future points. So for the network, it looks like an infinite grid of points, a repeating pattern, and it tries to connect it just somehow in order to, well, given we penalize producing line where it shouldn't be, less than not producing line where it should be, then it's biased towards producing more connections. But I've observed something interesting. So first of all, I've generated a couple of videos showing the system evolution for a batch, for a random sample, and we see this is the process of this network construction. So it starts slowly adding more and more nodes, and actually sometimes it even happens to hallucinate additional nodes where they shouldn't be, although the original nodes all located in, like, original nodes don't disappear. So watching this, I decided to see what would the result look like if I just start from all zero state. And here is a video of 15,000 iterations. So everything is dark at first, and then the system happens to hallucinate the dots out of nowhere. So in case there are dots, it connects them and sometimes populate empty areas, but leaves the original nodes intact. And if there are no nodes, then it happens to just hallucinate them out of nowhere. So we were trying to design a system that makes a spanning tree, but happened to make a system that is essentially a pattern generator, although we didn't have any texture generating objective. And I also tried to export so I turned this code snippet into a function, and I turned this cell automata into GLSL rule, and that's what it looks when I run it on Shader. I have a special extension that allows me to execute shaders faster than one step per frame. Now I'm writing 16 steps per frame. And we see that it started to hallucinate network that looks like those training examples that we were feeding into the cell automata, which is, well, when people ask about open-endedness, well, I don't have open-endedness, but I have a lot of unexpected behaviors. And also what we know about life, that it generalizes very well to situations that are widely outside of normal conditions that living systems exist. And even from evolutionary perspective, like there is no evolutionary pressure to develop some capabilities just because in wild nature living systems didn't happen to meet these conditions, but still they can sometimes adopt to situations outside of evolution regime pretty well. And here we see like strange unexpected adaptation when the system trained for one task does something else. Actually, I think if you want to avoid this behavior, in one of my other experiments, I tried to use a separate fixed channel to provide the location of seed nodes so that it didn't hallucinate them. So it was all constant, and in that regime, it was always just connecting the dots. And this notebook that we've made, I'll upload it to GitHub right after tutorial ends, and add all the link to this tutorial webpage. And then, well, I tried some other tasks with these models, and what I learned is that what task that can be solved starting from local neighborhood and then like spreading the influence work pretty well. For example, pattern recognition works pretty well. Well, maybe I have this experiment here. Task, no, yeah, this one. Like I was feeding the network with a mass of letters, a lot of overlaps, and it had to do two tasks. It had to spot letters Z, X, Y, Z, and then it had to connect them with lines. And it was quite very easy for network to filter out X, Y, Z. I was really surprised by how easy it was for the system to spot them and separate from this mass. But it couldn't build connection lines because well, it had to decide between, like, from Z it had to find X, and well, from Y basically it had to decide between which pairs of letters should it build lines, and somehow it didn't work, although maybe the restriction is just the size of the model. Remember that this is just less than 600 parameters, the size of the model that we are dealing with here. So all behaviors like patterns that we observe like when we do text to synthesis, or this behavior of detecting if there are nodes in one of the channel, and if there are nodes, then try to connect them with neighbors, and if there are no nodes, hallucinate some out of nowhere, and by breaking the symmetry, and then connect your own hallucinations. It all encoded in this less than 600 coefficients. And I also want to show another shader toy example and another demo before the end of the tutorial. So this is what I called, well, at some point I wanted to simplify things even further because I started, well, I was talking a lot about circuits in this tutorial, and I was trying to really come up with a representation of a model that would look like an electronic circuit, like a printed circuit board. And I realized that it's pretty non-trivial for me to route those filters if I wanted to be like two-layer, and it all looked very entangled. And then I modified the filters that are used by the model. I replaced them all. I removed. I'm sorry. Okay. So I replaced them with so-called, I called it side filter, which is just difference between center and nearby value. And I had 4 different versions of this filter rotated by 90 degrees. So essentially, it's just difference between me and neighbor and for corresponding channel. And 3 channels look up, 3 channels look down, 3 channels look left, 3 channels look right. And here is the shader toy implementation of this method. So now you see that there is only a single pass, and because perception and update were merged in a single rule. Let me post the link in chat. And I also put 2 patterns in the same shader. They are update rule 1 and update 2, and depending on time and pixel position, I switch between those rules. And here is what the perception boils down to. There is this like enhood function that reads 4 nearby pixels and selected 1 channel from each, and then the resulting result gets sent to one of two update functions and applied to X. I also quantize states to make sure that I'm able to run this on WebGL without floating point textures, because, well, I like quantizing. I like making sure that my models are as robust to various disturbances as possible. And finally, I'd like to show this demo. That's the same cell automata, but if we zoom in, then well, it's not finished. Not everything works properly. For example, those gray lines were supposed to visualize the updates as well, but what we see here is each cell is represented by this circuit. There are 12 nodes that correspond to those registers that hold state. And then there are these are perception nodes that compute the difference between state of own node and corresponding state channel of the adjacent node. So 3 wires go up, down, left, right, and then there is this matrix, and there are those forks. So this fork is when value is positive, it goes to the right. When value is negative, it goes to the left. And these little gray points that also I'm not visualizing, they should visualize the connection coefficients. They correspond to those nodes that take value of the vertical wire, multiplied by some coefficient, and add it to the horizontal wire. And then horizontal wires are connected to those feedback loops that feed the update value back to the those state holding registers, or like memory cells or whatever. And I actually think that this can be treated as a system of ODEs rather than a system with discrete time, and maybe even implemented as an analog circuit. So there will be probably a bunch of operational amplifiers and a bunch of resistors here. So I'm speculating a lot about ways to like substrates to deploy these ideas into the real world. Another substrate that I'm very curious about is something that I was presenting yesterday. This is reaction diffusion models, which is a version of cell automata, but restricted to using diffusion only to communicate. So it doesn't have perception phase at all. There is just a diffusion process that runs in parallel with the process of reaction, and reaction only knows the state of current cell. So this makes the system completely isotropic. That's why we had to develop a special loss that doesn't penalize incorrect orientation of the pattern produced, and we try to see that our models don't overfit to grid structure. So we trained a number of patterns, and only one of them overfit to grid structure, producing always the same diamond orientation. Other seem to be completely isotropic, producing patterns at different orientations in different runs. And we even experimented with varying the grid step size even on the same grid. And we do this by slowing down the reaction term in some areas that should be equivalent to using like either speeding up diffusion or using a fine, like non-uniform grid density, and it works as expected. We get patterns of varying density for all models except this one, which happens to produce unstable structures when grid resolution doesn't match the one during training, which suggests that this one happened to overfit to grid that used during training. And we observed that our models generalize to meshes that aren't 2D grids. They can easily be applied to three-dimensional meshes when we diffuse over mesh edges. And the most surprising for us, you can train a model in two dimensions and then run it in volume, because diffusion is diffusion everywhere. You just replace the diffusion in 2D with diffusion in 3D, and it happens for many models. It happened to produce coherent structures, like individual slices through the volume looked like target texture samples. And well, for this pattern, it somehow didn't work. It didn't. These line patterns didn't manage to stabilize in 3 dimensions, although it stabilizes in 2 dimensions. And you can reproduce all of these in Colab easily. There are even pre-trained models. So if you don't want to train your own, then you can just download pre-trained. Okay, we'll experiment with pre-trained models. So we'll just download in the pre-trained models, and then like you can run all the visualizations, generate all the videos, and for volumetric visualization, we actually basically here is how you implement the volumetric reaction diffusion with TensorFlow, and we even use our custom raycaster to do volume rendering, just because sometimes, pretty often, it's easier to write your own rather than agonizing on what library to choose. And the last project I want to mention that is not directly related to self-work, but is more about trying to look at the very, very basic elements that construct the systems we are building, like starting from NAND gates to computers. By the way, just wanted to recommend this course, which I actually didn't pass myself, didn't watch myself, but like it's very aligned with idea of understanding system from very, very tiny basic level to global scale. And the project I want to mention is this deepdream.c, which is implementation of oops, sorry. I'm using the wrong window. So this project, and which is implementation of convolutional neural networks and backpropagation to the image in like 900 lines of C code, and the only include that it uses is stdio.h. So in case you want to try to get an idea of how to implement the very, very simple, not optimized convolution and all other operations in a very low level and do backpropagation compactly, then may have a look at this project. Okay, I'm posting link as well. And finally, a few words about what are the next steps for differentiable self-organization. So I see 2 main directions of future work. One is applications, and another is modeling. So, actually 3. Okay, 3. Applications is trying to adopt these principles to a wider variety of tasks, potentially something that might be useful for in real engineering practices. Like, I don't know, robot swarms, or I actually dream about, genetically engineered weed that you plant your lawn and it produces some pattern, or dream about, decorative tiles that change their colors talking to their neighbors and can operate for thousands of years, so that like when archaeologists of the future uncover them in like 1,000 to 2,000 years, they see that our generation managed to produce living decorations that are absorbing energy from environment and organized to produce something beautiful. Well, another important direction is finding new modeling models to apply principles of differentiable self-organization. So I've started early experiments. Well, we've started early experiments with things like Physarum or slime mold model. I'm talking about Physarum polycephalum simulation. So this is a beautiful page by Sage Jensen that inspired my research in this direction. And I think that we can learn system like this, define local rules that lead to desired global behaviors for this type of models. And other types of models I'm interested in, say, reaction diffusion in 3D. Like, imagine you have some solution and you have some seed that grows in this solution, and there is a reaction diffusion process that happens on the surface of this seed and leads to aggregation of material from the solution on the surface of this seed, and can we program this reaction structure to grow the desired structure in 3D? So like, instead of 3D printing something, you just design the local interaction that produce the morphology, the shape that you want, and can do this like in scale. Well, and the third direction that I want to mention is like understanding the principles of operation of these models, because it's notoriously hard to predict the even for very simple models the mapping between parameters, and the result is very obscure, and I suspect that it just contradicts, well, it's basically something that the whole our culture of like sequential thinking, of decomposing things, just the way we think, don't allow us to understand the dynamics of these many interacting components. But with machine learning, I hope that there is at least some chance to design and maybe reverse engineer those systems. So that's all I had for today, and well, I hope we have maybe a couple of minutes for questions, although we are probably running out of time.